Okay, let's talk a little bit about temperature and rate. Most reactions will tend to increase in rate as the temperature increases. For example, foods spoil faster when they're not refrigerated. If you got two light sticks in water, one's in room temperature water, one's on ice, the one at room temperature will glow more brightly than the one in the ice because the reaction in the glow stick is occurring more quickly. The chemical reaction responsible for, say, the chemiluminescence in the glow stick is dependent on temperature. Higher the temperature, the faster the reaction. Therefore, the brighter the light. As the temperature increases, the rate will increase. Since the rate law has no temperature term in it, then therefore, as we've mentioned, the rate constant must depend on the temperature. So if we look at a rate constant increase of CH3NC going to CH3CN, we can look at that and we can see that in fact the rate constant does increase dramatically with temperature, so the rate will increase as a function of temperature. And so if we consider that reaction, the temperature increases from 190 to 250 and the rate constant goes from 2.52 times 10 to the negative fifth inverse seconds to 3.16 times 10 to the negative third inverse seconds. That's a quite dramatic increase in the rate, but why does that happen? According to the Arrhenius model, you have to have a minimum amount of energy to react. And that's because in order to form products, some bonds have to be broken in the reactants, and that bond breakage actually requires energy. And so we call that energy to kind of get the ball rolling the activation energy, because it's the minimum energy required to initiate a chemical reaction. So let's consider a rearrangement of acetonitrile. We form a transition state in the middle where the C triple bond N is rotating 90 degrees, and there's not much of a bond between that and the C and the CH3, and then it continues to rotate and forms a carbon-carbon bond instead of a carbon-nitrogen bond. So that intermediate substance between the two arrows is what we'd call a transition state or an activated complex. So in our case, the CH3NC, that bond tends to bend until it breaks, and then you get the nitrogen carbon triple bond portion is perpendicular. We call that, again, the activated complex or the transition state. That energy required for that rotation and bond breakage is the activation energy. Once that bond is broken, it can continue to rotate to reform a carbon-carbon bond, or it can go back to the original. And so if we look at that, we can see down here, this is our reactants here on this first flat spot, and it's going to go up. That bond's going to rotate until we get to our activated complex or transition state. The difference in energy between the reactant and the top of the hill is our activation energy. And then that bond can continue to rotate and we form products. The difference in energy there is our change in energy or our heat of reaction. That heat is going to be released because the energy of the products is greater than or is less than the energy of the reactants. And so that gives us the concept of an activation energy. So the change in energy for the reaction is the difference in energy between the reactant and the product. The activation energy is the difference between the reactant and the top of the hill. That means the reverse reaction would be endothermic. So once I form the carbon-carbon bond, it's less likely to go back once I've actually formed the product. This is based on collision theory. So if we look at the collision between nitrogen monoxide and nitrous oxide, if the N of the NO collides with the O of the N2O, then products are formed, N2 and NO2. If the N of the NO collides with the N of the N2O, then no products are formed. So we need to quantify that effect. There's a favorable collision and there's a non-favorable collision. So some of the collisions will go on to produce products, but not others. Temperature will increase the motion of the molecules, which will increase the number of collisions, but only a fraction of those will be favorable. So if we look, we've got going on to form products. with a favorable collision. The N and the O are colliding, and then the products go off their separate ways. Here, the O's collide, they just bounce off one another, no reaction. Here's another ineffective collision. The oxygen collides with the nitrogen, they bounce off again, nothing happens. The nitrogen of this molecule has to collide with the oxygen to get a favorable collision. And so some collisions are favorable but not others. Although overall temperature increases the total number of collisions, increasing the likelihood of getting a favorable collision, which does in turn to increase the reaction rate. So Arrhenius discovered that this process obeyed the equation. The rate constant is equal to A, which is a Arrhenius prefactor, measures the probability that we will get a favorable collision, and an E, which is a natural base like e to the x in your calculator, and it's raised to the negative EA, which is our activation energy, divided by RT, where R is the universal gas constant. In our case, since we're dealing with energy, it'll be 8.314 joules per Kelvin mole, and the T is the temperature in Kelvin, and it has to be in Kelvin for the equation to work, and A is just a frequency factor, it's a measure of the probability of a favorable collision. A and EA are specific to a given reaction. If we have a lot of data, we can get that graphically by rearranging the Arrhenius equation, take the natural log of both sides, and do a little algebra, and you get natural log of K is equal to negative EA over RT plus ln of A. So you'd get a line with slope of negative EA over R and a y-intercept of ln of A, where a y is ln of K. And you could plot the measured rate constant versus 1 over the temperature in Kelvin, and the line you get would help us get the activation energy and the A under given conditions. And so Y would be our rate constant, ln of A would be our B, negative EA over R is our M, our slope, and 1 over T is our X. But it's natural log and natural log. So it has to be natural logs because we pulled that out of the air, and we had to inverse the e to the x function. So if we have a lot of data, we could use it graphically, but if we don't, we can do sort of a 2-point, just using it in 2 points. So ln of K2 over K1 equals EA over R times the quantity 1 over T1 minus 1 over T2. And I distribute the negative into the subtraction there. So you can use that to actually, if you know the activation energy and you know the change of temperature, you could estimate K at some alternate temperature, is what that equation is good for. And that's the one we'll focus on a little bit more than graphing the equation. So what we're going to do is we're going to work that 2-point equation, ln of K2 divided by K1 equals EA over R 1 over T1 minus 1 over T2. And so we're going to use this reaction. 2N2O5 goes to 2N2O4 plus O2. And so the rate constant, K, is equal to 7.8 liters per mole per second. And so we'll call that K1. At temperature 673 Kelvin, we'll call that T1. Why is the rate constant at 703 Kelvin? That'll be T2. And then we'll solve for K2 with an activation energy EA of 111 kilojoules per mole. And remember, our R constant was 8.314 joules per Kelvin mole. So let's look at that particular problem. And so I've transferred all that information over. The first thing is you've got to fix one of these or the other. It really doesn't matter which. I'm going to do the R, but it doesn't really matter which. 8.314 times 10 to the negative third kilojoules per Kelvin mole. That way, because it's got to match or it won't work. It doesn't matter which one you do, but you've got to do one. Now, since I'm solving for something that's in the parentheses, I'm just going to leave that alone initially. So I'm going to say ln of K2 over K1 is equal to, now we're going to do our EA, 111 kilojoules per mole divided by 8.314 times 10 to the negative third kilojoules per Kelvin mole. And so the kilojoules and the moles cancel. We're left with 1 over Kelvin in the denominator. And that's okay, because we need it to cancel. And what we're going to cancel it with is our 673 Kelvin minus 1703 Kelvin. And then the kelvins are going to cancel. So we're going to need to run that through our calculator. And just leaving the rate constant alone for the time being makes the algebra just a little bit simpler, which is why I'm doing that. So let's run the numbers we got through our calculator. And so we get 0. I'm going to go 3 sig figs on this, 847. And that's a unitless number because I canceled all my units. But that's okay. And it's actually negative because, no, actually it's not as positive. Sorry about that. Because this number's smaller, so that ends up being a positive number. So what we have to do is now get that K2 out of the logarithm. So we're going to e to the x both sides. And so we get K2 over K1 equals e raised to the 0.847. Then multiply both sides by K1. So K2 equals K1 times e raised to the 0.847. Now I can plug and chug the rest. So we're going to put that in. Our K1 was 7.8 liters per mole per second, and times e raised to the 0.847. So we need to run this through our calculator. 7.8 times e raised to the 0.847. So K2 equals 18. We'll just keep it to 2 sig figs, liters per mole per second. And that would be our answer. And notice that it does go up when the temperature goes up, which is exactly what we would expect.